Hello, everyone, and thank you to Emma for that kind introduction, and thank you to everyone for dialing in today. As Emma said, the main subject of our talk today is hazards in low-carbon industries. Now, obviously, in the short time we have available today, it would be impossible to describe all the hazards in every low-carbon industry. So our plan today is that we will go through just a few examples and try to draw out some general themes and personal views relating to major hazard safety for low carbon industries. I think one of the reasons I was keen to give this presentation today is that although most people are well aware of the safety and environmental hazards associated with traditional oil and gas industries, there is often a bit of a perception that low carbon industries are intrinsically green and good and safe, perhaps, which isn't necessarily always the case. In the oil and gas industry, it's almost taken for granted that everyone at every level in an organization has safety ingrained in everything they do. And I'm a little less sure that the same is true in all low carbon industries. I think safety managers and engineers directly involved in the industry tend to be very well informed, but it doesn't always percolate all the way through to all levels of an organization. And I think the other factor is, public perception of, the low carbon industries is doesn't always recognize the hazards that may exist. So today I'm just going to say a few words about three low-carbon industries where we've done quite a bit of work, namely hydrogen, biogas and biomethane, and manufacture of lithium-ion batteries for cars or battery energy storage systems. And then Andy will talk about carbon dioxide and try to summarize some of our thoughts and experiences in terms of hazards and safety in low carbon. So Andy, next slide. So I'll begin by talking a little about hydrogen. The first thing I should say is that hydrogen is not a new or a novel hazard. We've been working with hydrogen for many, many years, and we're all familiar with the fire and explosion risks. In fact, I'm reminded of one of the first times I visited a chemical plant as a junior engineer about 30 years ago, and it was just a few days after they'd had an event involving hydrogen. They'd had a high pressure cylinder trailer in a fairly open outdoor area, and a nearby wall had been blown over in a hydrogen explosion. Clearly, what had happened is that there'd been a high pressure leak from the trailer, which had somehow ignited, resulting in a significant explosion. So there were two things that were a little surprising. First, there was no obvious source of ignition. And secondly, people at the time generally thought that releases of hydrogen in the open would disperse safely upwards and that damaging explosions in the open were unlikely. So, so it was an interesting event from that perspective. We now know that there are a variety of possible ignition methods for hydrogen releases and that high pressure releases can self-ignite. And we also know that high pressure jets can be explosion hazards, even in the open. And we can now do lots of fancy computational fluid dynamics, like in the drawing shown there, that I'm sure could replicate what I saw 30 years ago. But despite everything we've learned about hydrogen hazards and the huge amount of ongoing research, there are many international programs ongoing. People know about HySafe and HyTunnel and many other research programs. Hydrogen is now being produced and used in such a wide variety of situations that amongst operators, safety engineers, and regulators, there is still quite a lot of uncertainty regarding what are the most significant failure mechanisms in any particular situation, and what is their likelihood, which is essential knowledge for any risk assessment for design and planning. Is it catastrophic failures of vessels and equipment, or are the risks dominated by relatively small releases being ignited? I think the answers are not simple, and it depends very much on the specific circumstances. And it's this variety of applications that means that simple rules of thumb have yet to be well developed for hydrogen. I mean, in some recent studies that we've undertaken, we found that explosions at hydrogen installations can lead to higher overpressures and higher leak frequencies and risks than if it was a comparable natural gas type installation. So, the design rules of thumb need to be checked and verified with more detailed and sophisticated calculations specifically for hydrogen. But I think one of the most important factors is that hydrogen is increasingly being used as a fuel in a variety of industries, for trains, ships, vehicles, and in industry. And those industries may be less familiar with such major hazards. So it's the awareness of the safety issues which is the real key issue. And there have been incidents such as the explosion that happened at Sandvika in Norway. Only involved a few kilos of hydrogen, but resulted in quite a significant explosion. It just reinforces the importance of that safety awareness. So next slide, Andy. So another area where we've seen the introduction of low carbon hazards to industries that previously weren't familiar with such fire and explosion hazards would be biogas generation, where biogas is generated from organic materials such as at a sewage treatment works. So now we have some significant fire and explosion hazards at installations where previously the main hazards were probably to the environment. And we're seeing additional hazards associated with biomethane plants, where you're converting the biogas to biomethane, which can then be put into the gas grid. So installations now have significant volumes of gas, where previously they probably weren't used to dealing with those sorts of hazards. So this all means there are additional major hazards associated with new low carbon industries, and whilst these all can obviously be managed safely, some of these locations are located quite close to populated areas, so people both on site and off site are being put at risk in the interests of going green, which raises the interesting question of how much additional risk is society prepared to accept in the interests of saving the planet? I don't have the answer to that. It's a philosophical question. Next slide, Andy. Lastly, I'd just like to say a few words about the manufacture of lithium-ion battery cells, principally for use in cars. We're now beginning to build huge gigafactories in the UK capable of producing over 1 million battery cells per day, like the one you can see in the picture. That's over 10 a second. So whilst the hazards associated with a single cell are pretty small, these facilities can be huge, some of the biggest buildings in Europe, and they require significant quantities of hazardous raw materials as their top tier Cambridge establishments. And whilst the hazards are not very significant, they are quite novel. So, for example, the material used to coat the cathodes of the cells is highly toxic, and it's a very fine powder. So there are interesting hazards associated with handling that. It has to be handled very carefully. And the cells themselves can undergo thermal runaway, generating toxic and flammable gases. Again, not a problem if it's just one cell, but if you have millions in a large building, it can be an issue. So these are all sort of quite novel hazards which require sort of careful consideration during the design and location of such facilities. which brings me on probably to my next slide. Next slide, Andy. So I think the final point which I'd like to emphasize is that many of the types of low carbon industries that we're talking about today, whether it's hydrogen, biogas, biomethane, lithium-ion cells, they involve hazardous substances and require hazardous substances consent in the UK, which is essentially a planning permission from the local authority, just because of the large inventories of hazardous substances involved. And in the UK, the Health and Safety Executive will advise the local planning authority whether to grant permission for these facilities based on whether the risks are considered acceptable. So it's really important, when planning a new facility or pipeline, to be aware of the major hazards, as it could be a showstopper for development. So I think that's all I want to say. So I'll hand over to Andy to talk about carbon dioxide.
That's great, Ian. Thanks a lot for that. Okay, so I'm going to talk about another area that we've been involved in over the last few years, and that's hazards associated with carbon dioxide. As part of carbon capture facilities, infrastructure to capture, transport and store carbon dioxide will be required. It's well known that carbon dioxide has asphyxiant properties and also has toxic characteristics. It has, for instance, UK HSE specified level of toxicity, or SLOT, and significant likelihood of death, or SLOD, values. It is not, however, classified as a dangerous substance nor a dangerous fluid under the relevant major accident hazards legislation, for instance, COMA and the pipeline safety regs. In fact, 10 to 12 years ago, the HSE conducted a research report where it compared the land use planning zones for carbon dioxide pipelines and natural gas pipelines. This was assuming that carbon dioxide was a dangerous fluid under the pipeline safety regs. The HSE found these zones to be broadly similar between natural gas and CO2 pipelines. But that assessment by the HSE was conducted assuming that carbon dioxide was in its gas phase with both natural gas and CO2 at pressures up to 32 bar. With CO2 pipelines likely to be operating in the supercritical phase in the future, say over 90 to 100 bar, to meet with carbon targets, we believe that the balance will be tipped and land use planning zones around these high pressure pipelines transporting supercritical CO2 will be larger than natural gas equivalents if CO2 is eventually given dangerous fluid status. It is noted that land use planning zones are highly dependent on the failure frequency assumed, and that is worthy of further and future development considering the characteristics of supercritical CO2. Due to the potential hazards associated with CO2, especially supercritical CO2, we always recommend that any development considering transport or storage of CO2 should treat it as a dangerous substance and dangerous fluid in case legislation changes in the future, in order that this may future-proof the facility. Although in its beginnings in the UK, supercritical CO2 has been transported in the United States for a number of years. There are approximately 5,000 miles of pipelines in the US that transport CO2 in the supercritical phase. This is mostly for enhanced oil recovery, for instance, taking CO2 from extinct volcanoes, compressing it to supercritical conditions, then transporting it to oil fields through a network of pipelines. Although there are around 5,000 miles of pipelines in the US transporting supercritical CO2, this is dwarfed by the gas distribution network in the US that contains approximately 2.2 million miles of pipelines. It's worth noting as well that unlike the UK, the US has regulated supercritical CO2 and requires operators to conduct certain safety studies, identify high consequence areas, or HCAs, and prepare appropriate plans to prevent releases, and also plans if a release does occur. It's not often in the high hazard industries, especially a relatively new industry for the UK, to have a case study and recent incident to reference. In February 2020, a supercritical CO2 pipeline near the town of Satartia ruptured, affecting a number of members of the public. And I'm going to go into this incident in a little more detail now, as it is relevant to the CO2 industry in the UK and shows the issues with transporting bulk CO2 in pipelines. It should be noted that the next slides have been based on the Pipeline and Hazardous Materials Safety Administration's investigation report, released only a couple of weeks ago, and also public articles on the incident. So first of all, I'll go through a little bit of detail about the incident itself, and then describe the effects of the rupture and release of supercritical CO2. The pipeline that ruptured was a 24-inch pipeline operated by Denbury. It contains supercritical CO2. The pipeline ruptured at 6 minutes past 7 in the evening of the 20th of February. Within a minute of the rupture, the alarm activated in the Denbury control room, alerting the operators to an event. A further 7 minutes after the alarm, the pipeline valves had been closed either side of the rupture, some 10 miles apart, and the first responders were notified by the public about a green fog near the rupture. Due to the reports of a green fog, the first responders thought they were dealing with a chlorine gas release, so contacted the local water treatment facility. Eventually, it was worked out that it was a release of CO2, and instant response was set up to deal with that. 4 hours after the rupture, it was reported that the release had stopped. The PHMSA investigation concluded that due to heavy rain in the weeks beforehand, this caused a landslide and led to rupture of the pipeline. The photos are taken from the investigation report and show the break in the pipeline and an aerial view of the pipeline after the incident. Note, there is white dry ice around the release point. What about the effects of the rupture? The chart to the right-hand side shows the release point as a blue star. It also shows a 500-metre buffer zone around the pipeline, which Denbury had calculated based on third-party consequence modelling to allow identification of the high-consequence areas that I mentioned earlier. It also shows a topography in the area close to the pipeline. It can be seen that Satartia is below the level of the pipeline rupture point, and with the wind blowing from the southeast, the release migrated into Satartia. Within a few minutes, people were overcome in their houses, at a fishing camp near the Yazoo River, and cars shut off due to the lack of oxygen. Many people reported severe breathing difficulties. Drivers scrambled out of their vehicles, but were disorientated and wandered around. People driving along in nearby roads passed out while talking on mobile phones. 3 people were found unconscious in a car. The town of Satartia was evacuated, and in total 45 people sought medical attention. Thankfully, no one was exposed to lethal concentrations of CO2, and it's also believed to be the first major CO2 pipeline rupture to lead to public impacts. It's noted in the investigation report that topography was not considered in modelling. As I mentioned earlier, the investigation concluded in the last couple of weeks, and the findings were that Denbury's procedures and processes did not appear to address soil instability nor look at geohazards, and its aerial patrols did not identify geohazards as a concern at the failure point. The dispersion modelling conducted underestimated the affected area if a release occurred at that particular location. The CO2 dispersion was affected by atmospheric conditions and topography, and a release impacting Satartia was never considered credible. There was also a failure in communication from Denbury, with local responders contacting Denbury after the rupture 40 minutes after it happened, even though Denbury had received an alarm and had closed isolation valves. Okay, now I'm going to go into the last slide. So this kind of summarises what we have tended to find in the low carbon industries that we have worked in, and Ian and myself have kind of reflected on this over the last few weeks, and these seem to be the main points that we've got. The people in companies and organisations involved tend to be less familiar with major accident hazards. They don't sometimes have a track record in managing major accident hazards, and are certainly less experienced with management of process safety. The projects tend to be completed at breakneck speed, and that means that they're often designed in parallel with regulatory submissions. There are sometimes showstoppers when we get involved in the planning process, so there is definitely a need for this to be considered early within the project. These are novel, first-of-a-kind hazards with some of these industries. There are less go-bys out there for designers, operators, and regulators to follow. The operating scale means that there is a potential, for a large potential for major accident hazards being released. There are huge storage and transportation systems. There's also the issue of a transfer of risk. There's potential exposure of people and the public to these new hazards, but there is also the low carbon mandate that we've got. So could the don't advise against UK HSE decisions mentioned by Ian earlier be changed to suit? That's a question. The people skills are readily transferable from the oil and gas industry to other high hazard industries. Risk management is risk management, no matter the industry. There is a potential for other associated materials to lead to major accident hazards. For instance, there may be storage and use of oxygen at these facilities, and that also needs to be considered. And there is also phasing of operations and construction, which needs careful thought. A lot of the low carbon facilities that we get involved with are built early, then expanded, and expansion then leads to SIMOPS. So that's our presentation today. I hope you found it useful, and I'd like to thank you for your attendance.